Hey everyone, this is a redo of the material we covered in class on chapter 7.1, the introduction of trigonometry. This whole chapter is really important for laying the foundation of how to think about trigonometry. So the first part we did in class, it went okay, but the second half of this lesson had some technical issues, so that's part of the reason I'm redoing it here for you. For those of you who are seeing this for the first time, this is part of an OpenStax book, very similar to one called Pre-Calculus, but this is particularly based on the Algebra and Trig version of that book. It's called Algebra and Trig. And welcome. So let's get started here. As you can see, our objectives here, the NTK means need to know. What you need to know, our introduction to trigonometry, which is based on a lot of geometry vocabulary, particularly about angle measures, degrees and radians, converting back and forth between degrees and radians, some more vocabulary about coterminal angles, and a couple of formulas. So first, trigonometry just breaks down into two words. Trigon. Some of you may remember from geometry days in high school, polygon is many-sided figure. Well, the trigon is a three-sided figure, a trigon, and the word metric. Put those together and we get trigonometry, which is the measure of triangles. Or more broadly, we're going to be studying triangles. And triangles are everywhere. And the Vitruvian Man by Leonardo da Vinci found all of these proportions, and you can see triangles that relate to the proportion of the human size. They are in art, they are in geography, they are in computer programming, they are in dentistry, they are in physics and engineering. Triangles are everywhere. If you can study triangles, then you can break down complex problems and solve complex problems with these little fundamental pieces. So let's start off with some vocabulary. Some simple things. Idea of array. Array is just it's not completely a line. It's half a line. So it starts at a beginning point and it goes forever only one way. Now that's important because that's how we make an angle. An angle is made out of two rays, one ray and another ray with a common vertex. And so when we're measuring the angle, we are measuring the amount of rotation between one ray and the next ray. But that is our vertex point, is the joining of those two angles. When we study trigonometry, we're going to have a lot of unknowns. Those unknowns will be angles and sides of triangles, and typically we'll use X, Y, and Z and reserve that for our algebra. So when we get into the study of geometry and trigonometry, we're going to use Greek letters to identify our unknowns in trig, particularly for the angles. So you'll see like theta. I could maybe write that a little better. Alpha, beta, and gamma. In physics, you'll come across psi and phi. So they have a lot more angles that you'll study when you're in physics. But in our class, we're probably okay with just those four: theta, alpha, beta, gamma. Now, the idea of measuring an angle, I mentioned before, it's the amount of rotation. So how much turning does it take to turn an angle? One side to get to the other side. Now, when we are turning with a starting side towards an ending side, and we call this the initial side. And then where the measurement ends, we call that the terminal side. Those two words are relative because if I rotate the opposite direction, I can also measure this. And when I measure it starting here, this would be the initial side. And then this side would be the terminal side. That green's not showing up too well there. This will be the terminal side. If I started here and ended here, and this would make this side the initial side. Couple of more vocabulary words. There's a few specific angles. There's very specific features to them, and they have special names, like the right angle. It is an angle that forms a 90 degrees, so it has a square corner. A straight angle, it's an angle of 180 degrees. So if I start here and I go all the way around, straight over to the other side, that's 180 degrees. Acute angles are less than 90 degrees. So it might be an angle that looks like that. Obtuse is greater than 90 degrees. So it might be an angle that looks like this. And a quadrantal angle. These are quadrantal angles. It just means it's on an axis. So you're going to have 4 basic ones: the 0, the 90, the 90. The 0 is on the x-axis. The 90 starts on the x-axis, ends on the y-axis. The 180 starts on the x-axis and ends on the negative x-axis. And the 270 starts on the x-axis and ends on the negative y-axis. And of course, we could do 360 because it starts on an axis and ends on an axis. So these are all examples of quadrantal angles. Anything that lands on 0, 90, 180, 270, 360, or any multiple of those. As long as your terminal side ends on an axis, those are quadrantals. Okay, lots more vocabulary coming at you here. An angle and standard position. Now I forgot, if you're in class, you have access to a lecture note packet or the packet that's on my website. You can print this out, so you can be following along with this through the lecture note packet. But an angle in standard position is a very specific definition. And it takes an angle and joins it to the algebraic coordinate system. So if I just draw a random angle out in space, that's one thing. So it's just kind of an angle hanging out there. But this other angle is now on the XY axis. And that creates some powerful connections for us. But let's first of all figure out what it is, and then I want to talk about those connections. To be in standard position, the vertex must be at the origin. Second, when we measure, the initial side is the positive x-axis. And then we rotate towards the terminal side. And when we rotate counterclockwise, that is a positive measure. And when we rotate clockwise, that would be a negative measure. So, these are the conditions to have an angle in standard position. So, if I were to draw a couple of examples, this one has its vertex. 0, 0. So it has the correct vertex, but it does not start on the right initial side. So this is not an example. Here is one. Let's see. Here's a point here. And if I start this angle here and rotate from here, there we go. So there is an angle, and it's positive because I'm going in the counterclockwise direction, but it's not an example because it doesn't have, it's starting on the positive x-axis. That's okay. Positive x-axis, but it's not starting at the vertex. So not an example. On this diagram over here, way on the right side, we have an example of an angle in standard position. Here's another example in standard position because I started on the positive x-axis and I rotated to a terminal side. It just happens to be a negative angle measure. Okay, I mentioned the marriage or the connection between these two, and I want to talk just for a short moment about history, very loosely about history, but what's happened here is there has been a marriage of two great kingdoms. The geometry has gotten married to algebra. Now, roughly describing what happened at a time, there were people who were really good at geometry, and they couldn't communicate well with people who understood algebra. And there were other people who were really good at algebra that didn't cross-communicate well with people who had geometry. And then there was a famous mathematician named Descartes, whom you may also know from your philosophy classes, because Descartes was a famous philosopher as well. The expression, "I think, therefore I am," comes from Descartes. Well, Descartes was also the one who came up with this simple scheme of combining geometry to the coordinate system. So as soon as we add geometry, things like points in space, or angles or circles to the coordinate system, we have the XY coordinate system, we can talk about geometry in terms of algebra. And once we can do that, then we can translate geometric objects into algebraic equations. Prior to this time, there were a lot of roadblocks and dead ends and problems that could not be solved. But when mathematicians got a hold of this, math just exploded. And in like 50 years from Descartes inventing this little idea, calculus came about. And when calculus came about, it just started answering all kinds of questions in science. And ever since then, science has been exploding with new knowledge. And for 300 years, most of it is tied to calculus. And calculus came because of that marriage between this idea of geometry with algebra. Okay, just filling in a little bit of background story for you. But now let's get back to our vocabulary. Another vocabulary word here is something called a coterminal angles. It's two or more angles that have the same terminal side. You can see in the diagram here, the blue one and the green one are both coterminal. That means they both finish on the red side. The red side here is our terminal side. TS, terminal side. Here's another example. Here is a orange angle. This orange angle is also coterminal. So according to the definition, the orange one, the blue one, and the green one are all coterminal. They all end on the same terminal side. So we have multiple variations of terminal sides, coterminal angles, I mean. And we have a little question here that we can use some analytical thinking here to figure out. Theta is the green one, 800 degrees is the blue one. How much is theta? Well, we know they're both coterminal, and we know the blue one's 800. And we also know that the blue one went around 360 degrees. It's 360 degrees, but it went around 360 degrees a second time. And then it has to go a little further. Let's call that x. And so in this situation, x is the same amount as theta. So if I just take that 800 and subtract 720, I'm going to get 80. Oops. I'm going to get 80 degrees. So the green theta also has to be 80 degrees. Hope that makes sense. Now find a different theta that is coterminal to 80 degrees, and the theta has to be negative. Okay, well that would be exactly like the orange one I drew. So something that's coterminal to the 800, and that would be that angle there. Well, all of these are tied together. The green theta, the blue 800, the orange angle. And if we look at the orange one and the green one, I'm going to do this analytically now. The orange one has to be a negative measure because I'm going counterclockwise. So whatever the answer it has to be negative. But analytically, if you look at the orange and the green, the angle that's orange and the angle that's green they make a whole circle, which is 360. So we just figured out that the green one is 80. So if we kind of analytically think this through, so let's subtract the 80 off of 360. So the orange one has to be let's see, 360 minus 80, that's going to give me 280. But also realizing that the orange one is negative direction, so the orange one has to equal a negative 280 degrees. So it's just something that we're playing around with. I'm not like following an algebraic equation here. I'm just doing it intuitively. There are other ways we could have figured that out, but that's just one example of satisfying the question. So you could have come at that a different way, and maybe you spend a minute and see if you can come up with another way to come up with that solution. Next, I want to talk about angle measures and drawing angles and visualizing them. So you're pretty familiar, I suspect, with the idea of 360 degrees makes a complete circle. I don't know which ancient civilization first came up with this 360 degrees. Somehow I vaguely have a thinking that it's related to the Egyptians. But whoever came up with it, it's a great number. If you don't have a calculator, 360 is pretty nice to have because it's so easily divisible you can divide 360 in half, get 180. You can divide it in fourths and get 90. You can divide it in twelfths, and what is that, 30s, eighths, you get 45. You can divide 360 by so many nice numbers, by 2, by 3, 4, 5, 6, 8, 10, 12. It's just so easily divisible. So you can do a lot of mental math with 360 and come up with lots of different angles. Now, I encourage you to study this shape to see sizes and proportions. Notice the red angles are multiples of 30. So here here's a 30 degree, and here's another 30 degree. 30 and 30 is 60, and another 30 is 90. And then another 30 is 180, 120 I mean, another 30, and another 30 is 180. So that makes 6 multiples of 30 to get to 180. 1, 2, 3, 4, 5, 6. 45, similarly, it's a nice fraction. And when we take 45, well, we can take half of 360 and we get 180. Take half of that, we get 90. Let me change colors because the 45 is blue. So you have a 45 angle. A 45 and a 45 makes a 90. So there's 2 45s. 3 45s makes 135. And a fourth 45 makes 180. So you get all these nice fractions of a circle. Now, I want to encourage you to play around with this and get comfortable with it, because you'll want to sketch out good solutions to your problems. And if you have a 30-degree angle, it's nice to at least sketch it close to what it should look like proportionally. One last thing. What is 1 degree? 1 degree is 1/360th of a circle. So imagine a piece of pizza. I know, a whole pizza. And you cut it in half, and you cut it in half, and half, and you keep cutting it until you have 360 subdivisions. Well, over here, not all of these subdivisions are uniform, but if we go back to the 30s, we have 12 30-degree slices. And that would be kind of a nice proportional size if we were getting a piece of pizza, to have one that's a 30-degree cut. But then we would have to take that 30-degree cut and we would have to cut it 30 times more. 1, 2, 3, 4, 5, 6, 7, 8, 9. So by the time we cut that 30 times more, that little slice of pizza would be hardly edible. I can't even draw 1 degree because it's just too small. So even that angle is bigger than 1 degree, I think. So it's a very small slice. Just a little discussion to help you visualize what's going on.